Hello physics friends, Mr. Collier here. Today we're going to do some example problems for friction. I want to start off by just reminding you that there are two types of frictional coefficients. There's the coefficient of static friction and there's the coefficient of kinetic friction. Static friction is when an object is not moving and kinetic friction is when it is moving. And both of these coefficients of friction do not have units. They are simply a ratio of the frictional force to the normal force. And since both of those are measured in newtons, you get newtons over newtons, there are no units. Now for a sample problem. How much friction is present when a 35 kilogram child slides across snow on a sled of mass 3 kilograms if we know that the coefficient of kinetic friction is 0.14? So first let's take a look at the equation for friction. The frictional force is equal to the coefficient times the normal force. So we can solve for the frictional force, which is the question, as long as we know mu, which we do know, and the normal force. How do we know what the normal force is? So let's continue by drawing a little diagram. If we have a child on a sled, super classy drawing, I know, we know that gravity pulls them down. And we know that they don't fall because they're on a sled, they stay up. So there must be a normal force supporting them. Since they're not accelerating up or down, these two forces must be equal and opposite. So that normal force is going to be equal to the gravitational force acting on them. And the gravitational force is going to be equal to mass times gravity. So I'm going to substitute that in just a second here. So the normal force, as I mentioned, is equal to the force of gravity acting on the child and the sled in combination. So when we add their masses together and multiply it by the strength of gravity, we'll get the normal force. Next, we just need to take that normal force, which we calculated, and substitute it in for the normal force in the equation, use the coefficient of friction, and we will get the quantity of friction. That frictional force is going to be opposite the direction of motion, and so we want to indicate that. We can do that with a negative sign, or we can just do it by saying in the opposite direction. Next, we want to figure out what the acceleration of the child will be going with a mass of 35 kilograms if we know that coefficient of friction. So the net force causes the acceleration. Friction is the only horizontal force, so it is the net force, right? If the child is just sliding across the snow, again, a diagram helps, right? If they're just sliding across the snow, right, if that's the motion, then the only force slowing them down is friction. So friction is the net force. Net force is equal to mass times acceleration, and that is the frictional force. So we can rearrange it so that the acceleration is equal to the frictional force divided by the mass. We just determined the frictional force in the previous problem. We divide it by the mass, and we know how much they will accelerate. Now, knowing that acceleration, if we know their initial speed, we can also figure out how far they will travel before they stop. Again, because friction is the only force, right? Child on a sled, friction is slowing them down, so they're going to coast to a stop. To answer this, we're going to use a kinematic equation. We know the initial velocity and the final velocity, right? They're going to be going 5.4 to begin, and they're going to come to a stop. We know the acceleration from the previous question, and now all we need to do is plug in those numbers to find how far they will travel before stopping. So I plug in my numbers, simplify, and I know how far they will travel before they stop. I posed this like it was 3 different questions, but it would not be uncommon to see this as a single question that said, if the coefficient of friction is 0.14 and the child is going 5.4 meters per second and has a mass of this, how far would it be before they stop? And you would need to go through the process of calculating friction, calculating acceleration, and then calculating displacement. Or another question might be, if I wanted the child to keep moving at a constant speed rather than it slowing down because of friction, what force would be required to keep them moving at a constant speed? Well, since the frictional force was 52 newtons, then it would require an equal and opposite force so that the net force was equal to 0 to keep them moving with a constant speed so that the acceleration was 0. Here's another way we can ask a frictional question. Say you push on your 50 kilogram dresser with 500 newtons of force and it accelerates at 1 meter per second. What is the force of friction? So normally, we start with a free body diagram. We've got a normal force, a gravitational force. In this case, we have an applied force, and we've got a frictional force. Since it's accelerating, the applied force must be bigger. The question is, how much bigger? Let's calculate it. Since there is an acceleration, there must be a net force. The acceleration in 1, the mass is 50 kilograms, so the net force must be 50 newtons. In other words, the applied force must be winning, right? Must be above friction by 50. So let's spell that out in an equation. The net force comes from the applied force and the frictional force. The applied force is 200. The net force is 50. So how much must friction be? Well, it must be negative 150. Here's another sample problem. Say you push on your 100 kilogram refrigerator. It has a coefficient of static friction of 0.67. You push with 600 newtons, what will happen? So here we've got a normal force, a gravitational force, an applied force, and a frictional force. And the question is, if I'm pushing with 600, what happens? Does it move? Does it accelerate? Does it not move? Really, what it's asking is 600 newtons enough to overcome static friction? So, first, we're going to calculate the static friction. Friction is equal to the coefficient of friction times the normal force. The normal force, as I drew in the free body diagram, is going to be equal and opposite to the gravitational force, mass times gravity. The coefficient was given in the problem. So now I know that the maximum amount of friction that the refrigerator can create is 657 newtons. Since the applied force is less than that, we're not going to be able to overcome friction. So in this case, the refrigerator won't move. All right, let's say you push on your 30 kilogram desk and it requires 250 newtons to set it in motion and 200 newtons to keep it in motion. What is the coefficient of static and kinetic friction? So very similar, you've got this desk, right? It's got a gravitational force, it's got a normal force, it's got an applied force that you're pushing on it, and it's got a frictional force. Now, anytime it's moving in constant motion, these two forces must be balanced. The applied force must equal the frictional force. That's going to come into play as we go through this. So first, the maximum static friction, right, is going to be equal to that 250 newtons that it takes to set it in motion, right? And so that is equal to mu times the normal force. And again, that normal force is going to be equal to the gravitational force when those are both in the y-axis and they're balanced. So that's 30 times 9.8. That gives me the coefficient of static friction. And once it's in motion with constant speed, then we are balancing the frictional force of kinetic friction at 200 newtons of push with mu times the normal force. So in this case, for both of these, we were setting equal the applied force to the frictional force because there was an equilibrium, right? The applied force was equal to the frictional force to get it in motion and then to move it with constant speed. All right, almost done. We're going to do this in two versions, and then we'll wrap it up. Say you have a 100-gram sled going 2 meters per second, and it stops in 80 centimeters. What is the coefficient of friction? Okay, so one way we can approach this is by using the kinematics to solve for the acceleration. We know the starting speed. We know that it comes to a stop, so we know its final speed. And we know that it takes 80 centimeters to come to a stop. Using those, we can calculate the acceleration. Knowing the acceleration and the fact that the sled, right, the only thing stopping it is friction, right? It's got a normal force, it's got a gravitational force, but there's no other force. So therefore, the frictional force is the net force. The net force is mass times acceleration. So there must be a 25 Newton net force acting on it. That net force is the frictional force. Now that I know the frictional force, I can calculate the coefficient if I know the normal force. The normal force, since it's on a horizontal surface, is just mass times gravity. I can substitute and solve. Now let's say I had this exact same problem, only they didn't give me the mass of the sled. Can it still be solved? The answer is absolutely. I would still solve for the acceleration using the kinematic equations. Then I would set the net force equal to the frictional force. As I mentioned, the net force is the only force, which is the frictional force. So I can take mass times acceleration, net force, and set it equal to the equation for the normal force. Sorry, the frictional force. Now in this case, notice that there's an m on both sides, so the mass actually cancels out. And so I can simplify this equation to say that the coefficient of friction is equal to the acceleration that it experiences divided by gravity. And when I do that, I get the exact same coefficient. So there's a whole bunch of different examples of friction problems in one dimension. Good luck.